theory. Prior to that, we did valency bond theory. What were the latent features of valency bond theory? Can anybody tell me that? Salient feature of valency bond theory. What were the assumptions made in that? Yes, someone? Who gave this theory? Valency bond theory. And what were the major features of this? What was it based on? Come on. Someone from a group of 120 plus students. Come on. What were the important components of valency bond theory? What happened? We discussed it not too long back. What about Werner's theory? What happened in Werner's theory? What were the salient features in Werner's theory?
According to Werner's theory, Werner has described two types of valencies, primary and secondary valencies. Primary
Yes.
valencies are those which are ionizable, and secondary ones are those which are non-ionizable. And
Very good.
yes, ma'am.
Yes, very good.
Primary valencies are mainly primary valencies are denoted by the oxidation number of the compound, and secondary valency is a coordination number. And
very nice. Can I have a name, please?
Akshar Dubey.
What was it? Akshar.
Yes, ma'am. Akshar Dubey.
Thank you, Akshar. So you told us about Werner's theory. Very nice. Can somebody now explain the valency bond theory just in few lines?
Valency bond theory was proposed by L. Pauling, and according to it, it says that it recognizes it differentiates ligands as two types, one as weak and other is strong. So it says that the weaker ligands are do not what we say that they do not replace or compose the electrons to lower electronic shells orbitals, and the stronger ligands tend to do that. And, what to explain more?
And what was one of the salient features?
And VVT was able to explain the geometry of the complexes.
Yes. With the help of what?
Hybridization, ma'am, different
Hybridization. Yeah.
Yes. That is the word I was looking for. What did they treat? All the orbitals that were there. They say that which were the orbitals normally that they considered, which are going to interact with the ligand in the central metal atom. There's a central metal atom. And what are the orbitals of this central metal atom which are going to interact with the ligands? The vacant orbitals?
D orbitals.
D orbitals and the outermost, the 3D, 4s, and 4p.
4s.
3D, 4s, and 4p. These are the orbitals normally that are that would be made vacant or available for the ligands to share their lone pair of electrons with it. But we know that the shape of 4s is different, 4p is different, and 3D would be different. So you cannot have equivalent orbitals there. So he introduced the concept of hybridization there. That's right. Thank you. Who are the two who answered my question?
Ma'am, Akshar.
Akshar and
Arnav.
Arnav. Okay. So and with the help of this, can somebody explain to me what was, according to the valency bond theory, what is meant by an outer sphere coordination complex and inner sphere coordination complex?
Ma'am, in outer sphere coordination complex, outer d orbitals are included, outermost, and in inner d orbital complexes, ma'am, inside the orbital are used, ma'am, like 3D orbitals are used for
Well,
bonding.
that would be the inner, and the outer would be
For this,
4D.
ma'am, inner
Yes,
will be used, outer one will like
very
4D.
good. Who is that? Let me know your name.
Akshar Dubey.
4P.
Akshar. Okay. And so outer and inner. So this was also an important concept that he introduced, and he was able to explain with the help of this some of the magnetic properties. Explain why some are, if they are magnetic, then what is the structure. So correlating it, you had to know one of them. You had to know the experimental value of the this magnetic value in order to assign what would be the hybridization present there in that complex that is being formed, right? So, so that was valency bond theory. Now we are on to the crystal field theory. So here in crystal field theory, what are the assumptions that we have made? What have we assumed here? One of the most, and who was the person who gave this theory or who introduced this theory? Crystal field theory. You remember the name?
Bethe.
Yes, that's right. Hans Bethe was the person who introduced it. And as we discussed yesterday, that this was known for quite some long time. And but while we continued with the valency bond theory, it was simple and easy to use concept of hybridization. Using concept of hybridization, we could explain a number of features there in these coordination compounds, and very easy two-dimensional structures could be given. So it was easy to explain. So we continued using that. But while this had existed all along for a long time, it was normally used by the physicists. We were not using it. The chemists were not using it. But by the solid state physics people, they were using this. But now when it was applied here, so what were the major content of this? One of the major thing in this crystal field theory is that now you're using it much more widely as compared to the valency bond theory. Valency bond theory. What are the assumptions? Here it assumes that the attraction between the central metal atom and the ligands in a complex is purely electrostatic. Absolutely, purely electrostatic. So there is no question of any sharing, etc. There it is a purely electrostatic attraction wherein the ligands are treated as point charges. The negatively charged ions, they would be the point negatively charged ions. Central metal atom would be the positively charged ion, and the interaction between the metal, the central metal ion and the ligand is treated as purely electrostatic. The central metal atom, which forms the central atom in the complex, it is regarded as a positive ion of charge equal to the oxidation state. So the charge, positive ion charge, would be equal to the oxidation state of the central metal atom. And this is then surrounded by the negatively charged ligands. It can be negatively charged, or you can be neutral molecules, which their negative end of their the point which the part that would be facing the central metal atom would be where you have the negative end of that molecule, which has the lone pair of electrons present in it. So if the ligand is a neutral molecule, then the negative end of the dipole in the molecule is directed towards the central metal atom. And the electrons on the central metal atom are under repulsive forces from those in the ligands. So whatever the electrons present, they will be as the ligand is approaching. So initially you imagine the central metal atom to be, first let us look at we looked into the d orbitals, because mainly it is the d orbitals that are in play. So we looked at the structure of the d orbital. There are 5 d orbitals as we have seen them. The 5 d orbitals are dxy, dyz, dxz. And as we can see, the picture here is clearer, better. So look at this. This is the z-axis, this is the x-axis, this is the y-axis. And we find that the dxy means that the lobes of the orbitals are in between the axis. Similarly, in dyz, dxz, whereas when you look at dz squared and dx squared minus y squared, you find that they are along the axis. The lobes of dx squared minus y squared is along the axis, whereas the lobes of dz squared is also along the axis of the z squared. So these are the 5 d orbitals, and normally they are, we say that it is in a degenerate state. So this is the state that you find the 5 d orbitals. They are of the same energy, at the same energy level. Their shapes their orientation and space are different, but they are all equivalent. So an electron can be present with equal ease in either this or this or this or this or this, because all are of the same energy. So it can there is no difference here in which a single electron can reside in any one of them when they are in an isolated state. Suppose it was an M plus ion, so that metal would have 1 electron in the d orbital, and that would be here. If d1 we are talking about, suppose there is only 1 electron on this, say scandium in a +1 state. So it would be, this is how it would be here. It would have just 1 electron, it would stay like this in a degenerate state. When they are of equal energy level, we call it that it is in a state of degeneracy, meaning of equal energy. Now, as the the ligands start approaching, these are the ligands 1, 2, 3, 4, 5, 6. The 6 ligands are approaching towards the central metal atom. We are thinking that this is moving like initially it comes around as a spherical charge. So a charge of negatively charged sphere is formed around the metal atom. So as it forms that sphere, what is going to happen is that these are negatively charged. Our this outermost d orbital, if it contains electron, so that is also negatively charged. So there is a repulsion between the ligand that is approaching and the electrons that is present in the outermost orbit. So as a result of that repulsion, the energy of the d orbital gets increased. The energy of the high orbital of the d orbitals gets increased, so it moves up. We are still in the state of degeneracy, but what is going to happen? Suppose the field is coming and the 6 ligands are coming in an octahedral field. Okay, so an octahedral complex is being formed. So the spatial arrangement is an octahedron, and we are having, so an octahedron would look like, so this is the octahedral structure. This gives you the shape here. So this is behind, you can see in the water print, you can see this parallelogram, and you can see the apex there. So they are approaching along the X, Y, and Z axis. All 6 ligands are coming nearer, and they are approaching along the X, Y, and Z axis. Now what is going to happen is that the degeneracy is going to be lost. Here, this was degenerate at lower energy level. As the ligands start approaching, the degeneracy disappears, and you have the because of the 6 ligands, the spherical field that is formed because of the 6 ligands approaching, the energy of the d orbitals is increased. So it increases from the lower level to a high level. Still it is degenerate. Now as it approaches nearer, what happens is that those orbitals which are along the axis are going to face a greater repulsion as compared to those orbitals which are in between the axis. So we saw just now that dxy, dyz, and dxz, their lobes are in between the axis. If it is in between the axis, that means they are not in the direct line of attack. So neither in the dxy, nor in the dyz, nor in the xz would you have a greater repulsion. So they become lower in energy because there would be less of ligand and the d orbital, the electron, if it is present in this orbital, it would be less of repulsion because of that. So if they are away, then they become lower in energy, whereas those orbitals which are in line, direct in line with the ligands as they are approaching along the axis, they become higher in energy. So now we say that the degeneracy is lost. The degeneracy that was there because of the approach of the spherical field, now as they approach it, because of the shape of the various d orbitals and the spatial arrangement of these d orbitals, we find that the dxy, dxz, and dyz, they get lowered in energy. So 3 of the d orbitals get lowered in energy, whereas 2 of the d orbitals get increased in energy. And that increase in energy is as much equivalent to the amount of decrease that is there because of these 3 orbitals that are reduced in energy. So we call this difference in energy between the 2D levels in a given is given with the symbol of either this delta O standing here for the octahedral, or you can either call it as 10 dq. It is given as the sum total as 10 dq, and it follows that the Eg orbitals are 0.6 times a delta O above the average level, and T2G are minus 0.4. So this gets these of these 5 orbitals, this gets lowered by 2/5, whereas this gets increased by 3/5. So this is the increase here is 3/5 times the decrease that is here. So the increase here is of 0.6 delta O, and the decrease here is of minus 0.4 delta O. So we give this as plus 0.6 delta O, that is an increase in energy by the amount that is lowered here. So this much lowering. So this is increased by 3/5, and this is lowered by as much as this is increased. So by 2/5. So this is minus 0.4 delta O, and this becomes plus 0.6 delta O. So, and this thereby, and this is the average. You call this as the barycenter. This is the average energy center that is maintained, which gives you the center of gravity at this level. So as much increase here is balanced by as much decrease is there. Thereby it remains as 10 dq, and this increases 0.6 delta O. This decreases minus 0.4 delta O. So this is about the splitting and this energy level degeneracy that is lost. We say that this becomes triply degenerate, meaning and this is T2G we call it as, and triply degenerate, meaning all 3 of these d orbitals are equivalent in energy at a lower level, and by how much? Minus 0.4 delta O. And these are doubly degenerate, meaning these 2 are increased in energy. They are at same equal level, but at a higher level, and this increase in level is 0.6 delta O. Okay. So this T2G, that is triply degenerate set of orbitals, and EG is doubly degenerate set of orbitals. G stands, it is a gerade, as we discussed that earlier. It is symmetric with respect to the center of inversion, and U is ungerade, that is antisymmetric with respect to the center of inversion. So because octahedral molecules have a center of symmetry, so we use the word gerade there. And when we discuss the tetrahedral, we'll not use the word G there because it does not have center of symmetry. We're not going into details of this because we are not studying symmetry right now. Suffice to remember, G is gerade, that means symmetric with respect to the center of inversion, and U ungerade, antisymmetric with respect to the center of inversion. And the term barycenter is a point between objects where they balance each other. And the word DQ, as you can see there, the word DQ I mentioned somewhere, and it is, you call it as differential of quanta. It is differential of quanta energy, or it is a quantum mechanical description of the electrostatic model of crystal field. So it is this dq. In this, it is the differential of quanta and energy, and it is a quantum mechanical description of the electrostatic model of crystal field. So we will, you can use either 10 dq or just call it as delta O. Okay. We were looking into, yes, we looked at the d orbitals. We looked at how the ligands are approaching here in the dx squared minus y squared, dz squared, and we saw the three degenerate T2G orbitals. So these are the orbitals, the EG orbitals, these are the T2G orbitals. And we have seen that the repulsion between the ligand lone pairs and the d orbitals on the metal results in a splitting of the energy of the d orbital. And the splitting is shown here, delta O. This is this 3/5, the amount increases, plus 3/5, and this is minus 2/5. So this becomes 0.4 minus 0.4 delta O. This becomes plus 0.6 delta O. Yes, in this in some texts, the gap in the orbital, the orbital is assigned a value of 10 dq. The upper EG set, it goes up by 6 dq, and the lower set goes down by 4 dq. The actual size of the gap varies with the metal and the ligand. So what the difference would be, it depends upon the metal in which oxidation state it is. It depends upon whether it is 3D, 4D, or 5D, or and also it depends upon the ligand, the type of ligands that are present, whether it is a weak ligand or a strong ligand, that the gap that is there, how much of splitting is taking place, that is given as, and the term that we use for the splitting, because of the presence of ligand, when the degeneracy is resolved, the ligands, as the ligands approach, the splitting of the d orbitals between EG and T2G, the difference between the two would depend upon if the ligand is a strong ligand or a weak ligand. A weak ligand may cause a less amount of splitting between the d orbitals. A strong ligand will cause a higher amount of splitting between the two orbitals. So depending upon the type of ligand that is approaching, you would have the value of the delta O changing. 10 dq, it implies the differential of quanta, implying the energy, and d is a spectroscopic term where L is equal to 2. Color we'll see later. Before that, let us look at the crystal field stabilization energy. And then you have what is termed as high spin and low spin complexes. Okay, by high spin complexes, we mean that greater number of unpaired electrons. A greater number of unpaired electrons, meaning magnetic in character. So whether we can look into and see how why a compound is known as, any complex will be a high spin complex if it has more number of unpaired electrons. It will be a low spin complex. It is a low spin complex, meaning less number of unpaired electrons. So let us look at some of the complexes. Let us see, suppose you have titanium +3. It has got only one electron in it. So titanium +3 oxidation state, the number of electrons present is just 1. So naturally, where will this electron go? Unlike before, when the ligand was not approaching, at that time, it was degenerate. So this electron could have gone in any of the orbitals. But as the ligand approaches, what happens? The degeneracy is split, and you have two set of orbitals. One is a lower energy level, one is a higher energy level. And we know that in nature, everything tends to occupy minimum energy level. So the electron will go into it finds that the T2G orbitals, they are degenerate. So this is lower in energy than the EG. So definitely the electron goes to the DXY or DYZ or DXZ. Either of these it can occupy. So it stays here. So it is a high spin complex, meaning it has one unpaired electron. Now another one, suppose you have titanium +2, where 2 electrons are there. Again, the option is there. It has DXY, DYZ, DXZ. It will occupy this. And we know that they tend to occupy singly. They don't want to pair up because pairing up would need repulsion, overcome that repulsion amongst the 2 electrons. So they don't want to do that. And they would definitely like to, if one is taking DXY, the other will take YZ or XZ. That is a no-brainer. So it will come here. It will definitely not go there. Then and there's another complex, suppose it is vanadium in +2 oxidation state, D3. Suppose that means 3D3 here means that there are 3 electrons in the d orbital. Again here, 1, 2, 3, definitely they will, each one will occupy DXY, DXZ, DYZ. Again, no issue there. So there is no fight here, no struggle in this. They will each occupy one each at the lowest level. Now comes, let us say, chromium +2, wherein you have D4 electrons. There are 4 electrons. So obviously you'll find first they will occupy, the first 3 will go and occupy DXY, DXZ, DYZ. Now this done, what will the 4th one do? Now the fate of the 4th one will depend upon, right now 2 factors are there. In fact, it would depend upon 2 factors. One of the factor is what is the difference in energy between these 2 levels. This EG and T2G level, this level here, the difference for you had 1, 2, 3 electrons occupied here. Now the 4th one, the option is either it pairs up or it moves up. Okay, it goes to the EG level. So the decision has to be made what is going to happen. Suppose it was a weak ligand. If the ligand is weak, as I said, that this difference in energy depends upon the type of ligand it is there. If the ligand is a weak ligand, then what is going to happen? This energy difference will be much less. And if this energy difference is much less, or lesser than the energy that is required for pairing up of the electron, then what will it do? It finds that if for pairing it needs, let us say, 10 kilojoules of energy. But for moving into the next empty orbital, although it is a higher orbital, but if it needs 8 kilojoules, it's an arbitrary term that we are saying. So energy to pair up was suppose 10 kilojoules and energy to move to a higher level was 8 kilojoules. Again, we know that in nature, they want to optimize their energies. So they want to go to a level in which we are spending less energy. So here they find that, okay, if I move up here, that is better than trying to pair up, because I'm losing less energy, I'm not consuming more energy. So the electron will move up to this. So depending upon, or sometimes it may happen that if you have got a very strong ligand, which has caused a huge difference in the energies here, the value of delta O is much higher. Suppose the value of delta O is 12, if the splitting is more here. Then, and here it is, pairing up is only 10. Then definitely it will go for pairing up. So depending upon which of the options it has, depending upon the type of ligand that is there, which will decide upon this delta O value. And this delta O value is known as the crystal field stabilization energy, CSFE, crystal field stabilization energy. So this value again depends upon the type of ligand that is approaching. So the option whether it will move, this electron here will move into this orbital or this orbital would depend upon the type of ligand that we have. So here it finds that if the energy difference is less here, then the electron tends to occupy this orbital. So all these we are having, and since we have unpaired electrons here, all are high spin complexes. Here delta O is less than the pairing energy. So the condition here we can see is that the crystal field stabilization energy is less than the pairing energy. That is why this fourth one tends to occupy the EG orbital rather than pair up here. But if it was more, if the delta O was more than the pairing energy, then this would not have any other option. It would have to pair up here. Then in that case, it would not be unlike this complex, which has all four unpaired electrons, we would have only two unpaired electrons. So again, the decision whether it will be a high spin or a low spin would depend upon the whether delta O is less than the pairing energy or more than the pairing. Okay, now we have somebody's mic is open, so it's muted so that others can hear properly. Request you to mute the mic. It is being muted. Please check that the mic is muted. Thank you. Okay, so that was the case when you had 4 electrons. Now what happens in the fifth electron? Fifth electron, again, the same options. Examples are given here, which ions would have Mn plus 2 would have D5, Fe plus 3 would have D5. So here you find that 1, 2, 3, definitely they'll occupy dxy, dxz, dyz. The next one would occupy dz squared and dx squared minus y squared. So they are now half-filled. We have also studied about the extra stability of the half-filled orbitals. So maybe the presence of these singly occupied electrons in all the 5 orbitals gives it extra stability. So they would occupy singly out here. Next comes the next option now. You have wherein you got 6. D6 means 6 electrons in the d orbitals. Now, what is the option here? There's no other option in this. It has to come and pair up here. The pairing has to be done because other than that, it can have no other option. It has to pair up here because these are all singly occupied. So definitely the next option would be to pair it up here. So it pairs up here. Okay. And another option here is when you have 7 orbitals. So 7 pairing up takes place here. And again, that as in this, we have seen that the options are again just like this. Here pairing can take place. Here what would happen if this was very high? Again, the option was that if it was very high, delta O was much more, then they had no other option. If it was not conducive to them, it were not getting that extra stability. So that means it had no option but to pair up over here. So it would pair up here and give you a low spin complex, unlike this, which is a high spin complex where you have got 5 unpaired electrons. Here it becomes a low spin complex because the delta O value is much higher than the value of the pairing energy. So trying to jump up to a higher level, it required more energy than trying to pair up. So pairing up, the energy required was less, whereas jumping to the high orbital was much more because this difference, because of the ligand, this ligand had, whichever ligand was present, it was causing the energy level to increase. These are the symbolic figures. Here, I'm not trying to show you that all are same delta O's. So we are just depicting it as such, but here it is pairing. The fact that it is pairing up, it means that the delta O is much more than the energy required to pair up. So it spends some energy to pair up rather than move up and stay single. In this, the same thing happens. So this becomes, if this complex will become diamagnetic in nature because all of them are paired up, unlike this, in which it has 4 unpaired electrons. This is having, so depending upon the ligand, the ions oxidation state is the same in both. Here you have iron N plus 2, cobalt N plus 3. But if the depending upon what ligand is there, now we can have, if the delta O, because of a strong ligand, if the delta O becomes more, then pairing will take place and we'll have a low spin complex. But if if the ligand is weak and the crystal field stabilization energy is lower than the pairing energy, then it would stay independent. So we can get a high spin complex. So whether it is in this or in this or in this, you would have the same option. Here the option is not much because definitely you have only three of them, 1, 2, 3. So the problem is not there. No matter what complex is there, there is enough of space here in the d orbital. So they tend to occupy the dxy, dxz and dyz. But here they have an option depending upon the type of ligand. If the energy delta O is crystal field stabilization energy is higher, then definitely it tends to pair up and give you a relatively low spin complex as compared to this high spin complex. So chromium +2 state can form a high spin complex 2 as well as a low spin complex 2. Similarly, manganese +2 and iron +3, they can form high spin complex 2 and a low spin complex 2, depending on the ligand that is approaching it and leading to giving you crystal field stabilization energy, whether it is high or whether it is low. So how much of the splitting is there? So whether the splitting energy is more than the pairing energy, that will decide whether we get a low spin complex or a high spin complex. So the terms you should understand: what is pairing energy? Pairing energy means the energy required to put the electrons into the same orbital. Two electrons occupy, unlike the Pauli's exclusion principle, wherein we know that they tend to occupy individual orbitals, stay as far apart from each other, and instead of changing the spin, either +½ or -½ you depict it with arrows, arrow pointing up +½ arrow pointing down -½ So trying to pair them up, it needs energy, but that energy would depend upon whether the delta O is more or the pairing energy is more. So pairing energy, what we understand by the term high spin, low spin. A high spin complex means it has the electrons arranged, the d orbital electrons arranged such that they are occupied singly. So they give you high spin complex. If they pair up, they are low spin complex. So compared to this is a high spin complex. This is a low spin complex. These would be paramagnetic, but the one here with the low spin, it is diamagnet because all are paired up, and it is. So this is a similar example would be here. Now you have all these, the lower levels have got filled up in this. Let us see this cobalt +2, where it is D7. So D7 meaning first, how do we start with the filling? 1, 2, 3, 4, 5, then comes 6, then comes 7. So then the pairing will start. First they will occupy singly, and then as per the Hund's rule of maximum multiplicity, you would have first single occupation, then you would have the pairing up taking place. So this would be when the crystal field stabilization energy is not more. But if the crystal field stabilization energy is very high, then what will happen? Then that first electron goes here, second electron goes here, third electron goes here. Then the fourth electron has to pair up, fifth electron has to pair up, sixth electron has to pair up, and the seventh electron, of course, has no option but to spend that energy and move up. So it will be definitely a low spin complex because there is only one unpaired electron present here, whereas in this you have 3. So a D7 ion, say like cobalt 2, can have a high spin complex as well as a low spin complex, depending upon the type of ligand that is there, how much of energy is being spent, whether pairing is convenient or staying apart is convenient. So depending upon the delta O value, and that delta O value would depend upon the ligand that is there. So that is in the D7. Similarly in D8, you come to D8 again, 1, 2, 3, 4, 5, then the 6th one, 7th one, 8th one. It comes up here. And this again, there is no other option here because you don't have any other alternative here. So a nickel in a D8 state would have all the T2G orbitals filled up, and the dxy and dyz would dx squared minus y squared and dz squared would be singly occupied. Similarly, so the option of high spin or low spin question doesn't arise because these have already got filled up. Similarly, in copper, you have again copper in +2 state means a D9 ion. A D9 ion also has no options but to here it gets paired up here. Okay, and again in zinc, which has got D10, zinc +2, you would have, again we have no option, it would be all filled up. So the options here is between the D4 and the D7 that it can vary. It can be a high spin or a low spin complex depending upon the pairing energy, depending upon the delta O value. So understand the concept of high spin, low spin, when a low spin will arise, when a high spin will arise, what are the options available. So depending upon the energy difference, the delta O, and how we should be able to calculate delta O values. I'll do that. We'll do that in the next class. We'll try to calculate what is the delta O value using the number of electrons present in T2G orbital and the number of electrons present in the EG orbital. It is a simple method whereby we can calculate what is the crystal field stabilization energy. So in the next class, we'll look at the calculation wherein we can do the crystal field stabilization calculation related to the crystal field stabilization energy. Okay. So this is how we put it. We put it as crystal field stabilization energy is the value here, the point, suppose you call it as X, the number of electrons present in T2G. I think I'll take it in the next class. Let's leave it here at this point. We will resume the class on Monday, and I will deal with crystal field stabilization energy, how to calculate it, and then look into the significance of this crystal field stabilization energy. Some of the significance that many of the properties of the central metal complexes could not be understood, why there was variation in properties, like many such properties are there that gets changed, that changes. We will study all that and we'll look into all that in the next class. Okay, thank you. Go through what we have studied today so that we can do it. Okay, then.
Thank you, ma'am.
Yeah.
Thank you, ma'am.
Thank you, ma'am.
Okay.